So let's move on to kurtosis. Within this same descriptive statistics table, we see our friend kurtosis right underneath skewness. Now technically, kurtosis is the combined weights of the distribution tails relative to the distribution. So let's take a look again just for reference. You don't need to worry about these. These are kind of like vocab words. But in the future, if you ever need them, I just like to remember that platykurtic kind of sounds like plate, so that's going to be your fatter kurtosis here, and these are more relative to a negative kurtosis value. So in like a layman's terms, you could say that kurtosis kind of refers to the fatness of the distribution as a whole, right? So it is measuring how the data are clustered around the mean. So a negative kurtosis statistic means that your data is less clustered around the mean. You can see that in this green, in this fat distribution down here. Mesokurtic distribution is normal, middle, meso, right? Again, you don't need to memorize these. These are just kind of ways to conceptualize. So this red distribution, or the distribution in the middle, is a normal distribution. And this example, in this normal distribution, your kurtosis value in SPSS would show up as 0. Generally, sometimes when people are talking about kurtosis, or you're in a different statistical computing software, sometimes a normal kurtosis value is 3. But within SPSS, it's 0. It's just like skewness, so just keep that in mind. And then leptokurtic values, you can kind of think lepto as long, and those represent a more positive kurtosis statistic. So a positive kurtosis statistic would mean that more of your data is gathered around the mean, so it's more centrally located, which means this guy is why it's taller and skinnier. So let's take a look with that in mind at our output data here. And again, I'm just going to go over male data. You can apply the same concepts to females when you review this data yourself. So again, this sample size is around 50, so we can use that positive or negative 1.96 as a reference value. That 1.96 number just comes from using the 0.05 alpha level that corresponds to it. So let's take a look. Our kurtosis, and we're going to do the same thing we did with skewness. We're going to take the ratio of our kurtosis here. So it's 7.015 over its standard error, which is 0.845. And that gives us a pretty big kurtosis statistic here. And like I said, we're using that positive or negative 1.96 as a reference value. So in this situation, since this is much larger than 1.96, we would also have to reject normality. So we know so far this data is probably not normally distributed. To know for sure, we'll move on and talk about our Shapiro-Wilk test in the next video.